Lesson 17.1, Angles of Rotation and Radian Measure. Essential question, what is the relationship between the unit circle and radian measure? First off, what is the unit circle? Let me draw you one real quick. You've probably not ever seen one. We'll draw a little one right over here. And get a circle. I didn't hit it right on there, but I got close. Okay, so this point right here, that's going to be 1, 0. And this point right here is going to be 0, 1. And this point here will be 0, -1. And then, of course, this point over here is going to be -1, 0. Well, I'm having a hard time writing. That's going to be -1, 0. And that's 0, 1. All right. If you hadn't noticed yet, the distance from this center here to any point on this is r equals 1. The radius is 1. The distance from the center to any point on that circle is 1. That's why it's called the unit circle. All right, drawing angles of rotation and finding coterminal angles. In trigonometry, an angle of rotation is an angle formed by the starting and ending positions of a ray that rotates about its endpoint. The angle is in standard position in a coordinate plane when the starting position of the ray or initial side, and we'll say the starting, right here, the end point here is here at 0, and the starting position here, the starting position is on the initial side, is on the positive x-axis, and it has its endpoint at the origin. So that should be the initial side. To show the amount and direction of rotation, a curved arrow is drawn to the ending position of the ray or the terminal side. So we'll say this over here, this ray here, that is the terminal side. Okay, and then you draw a curved arrow. You draw a curved arrow like this, and that's shows the direction of rotation. That shows the direction of rotation. Notice if it's counterclockwise, it's positive. In geometry, you were accustomed to working with angles having measures between 0 and 180 degrees. In trigonometry, angles can have any measure greater than 180 degrees or even less than 0 degrees. To see why, think in terms of revolutions or complete circular motions. Let theta be an angle of rotation in standard position. And this symbol here, that symbol there, is called theta. It's a Greek letter. If the rotation for an angle theta is less than 1 revolution in a counterclockwise position, counterclockwise direction, then the measure of theta is between 0 and 360 degrees. And the angle of rotation measured clockwise from standard position has a negative angle measure. Okay, so what they're saying here is if we go this direction here, counterclockwise, it has a positive. If we go clockwise here, start at the initial side and go to the terminal side, clockwise, it has a negative measure. Coterminal angles are angles that share the same terminal side. Remember we said a minute ago that this here was the terminal side of the angle? That was the terminal side. Okay. Coterminal angles are angles that share the same terminal side. So these two angles are coterminal. If the rotation for theta is more than one revolution but less than two revolutions in a counterclockwise direction, then the measure of theta is between 360 degrees and 720 degrees as shown. Because you can have any number of revolutions with an angle of rotation, there is a counterclockwise angle of rotation corresponding to any positive real number and a clockwise angle of rotation corresponding to any negative real number. Okay, so yes, that's 420 degrees. But if you only go from here to here, that's 60 degrees. Okay. And likewise, if you go here and back around that way there, that is negative 300 degrees. Okay. All right. Draw an angle of rotation of 310 degrees. In which quadrant is the terminal side of the angle? So remember, if we start here, that's 0, right? When we get all the way up here, that's 90 degrees. Over here is 180 degrees. And down here is 270 degrees. And then back up to that line would be 360 degrees. All right, good. Now, so 310 degrees, well, that's between 270 and 360. So that's going to be down here in the fourth quadrant. That's going to be down here in the fourth quadrant. So let's take 360 and we'll subtract 310 from it, and we get 50 degrees. Well, we know from here to here is 90 degrees, so half of that would be 45. So it's going to be a bit more than 45. So we'll go, let's try to be straight. So 310 degrees, we're going to start here, and we're going to go all the way around here, and that's 310 degrees. All right. On the same graph from the previous step, draw a positive coterminal angle. What is the angle measure of your angle? So a positive coterminal angle. So it has to stop here. Well, let's see, let's start here. And so that's 360 degrees. And we come back around here, and what is that? Well, let's see, 360 degrees plus 310 degrees, I get 670 degrees. So this one is 670 degrees. So that's B. C, on the same graph from the previous two steps, draw a negative coterminal angle. So let's draw a negative coterminal angle. We're going to start here, and we're going to go clockwise, and we'll stop right there. Well, how far is that? Well, let's see. That would be 360 degrees minus 10 degrees. That gives us 50. So we're going to call this negative 50 degrees. And the negative just tells you the direction. If it's positive, you're going counterclockwise. If it's negative, you're going clockwise. All right, so that's A, B, and C. Reflect. Is a measure of an angle of rotation in standard position completely determined by the position of its terminal side? And the answer to that is no, and we just saw that. We had one terminal angle there, right? And we went around and we measured at 310 degrees. We went completely around again, and that was 670. And then we started the initial side and went clockwise and found that negative 50 degrees. So that was 3, and we were really just getting started. So we could say no, there are infinitely many angles of rotation both positive and negative, that can be drawn in standard position my handwriting, standard position with a given terminal side. All right. Number 2, find the measure between 720 degrees and 1080 degrees of an angle that is coterminal with an angle that has a measure of negative 30 degrees. In addition, describe a general method for finding the measure of any angle that is coterminal with a given angle. So if you do 1 revolution, that's 360 degrees, right? If you do 2 revolutions, that's 720 degrees. And if you do 3 revolutions, that's 1080 degrees. All right, and you can keep on going, just add 360 to the last one, and it goes around and around. Okay, you want to find something between 720 and 1080, and it has a measure of negative 30. So let's see here. We've got, let's draw us a little one right over here real quick. All right. So it's going to have negative 30 degrees. So that's going to be about 1/3 of that right there. So we'll say that's right there. So we start here and we go around. That's 360. That's 720. And then we stop right here. Remember, if we stopped there, that would have been 1080. So we can take 1080 degrees, subtract 30 degrees from it, and that's going to give us 1050 degrees. So that's 1050 degrees. Not too hard, not too hard at all. Understanding radian measure. The diagram shows 3 circles centered at the origin. The arcs that are on the circle between the initial and terminal sides of 225 degrees central angle are called intercepted arcs. So let's see here. Remember this right here. Let's see here. Let me get this, and let's get a little bit thicker. Let's draw. This is our initial side, right? And this over here, we'll use red. That's our terminal side, right? Okay. So we're going to start, and it says AB is on a circle with a radius of 1 unit. So AB right here, that's on a circle of 1 unit right there. AB is on a circle of 1. That means the distance from here to there is 1, no matter where you do. CD is on a circle with a radius of 2. So we're going to go and that's CD, right? So CD is on a radius of 2. And EF, that's this not here. And let's see here. EF going to be out there. So EF is on a circle with a radius of 3. Notice that the intercepted arcs have different lengths, although they are intercepted by the same central angle of 225 degrees. You will now explore how these arc lengths are related to the angle. The angle of rotation is 225 degrees. So 225 degrees counterclockwise. There are 360 degrees in a circle, right? 360. So let's see, 225. So let's do this. 225 divide 360, and that's 5/8. Okay, so 225 degrees represents 5/8 of the total number of degrees in a circle. All right. So each length of each intercepted arc is, and we'll put that right there, is 5/8 of the total circumference of the circle that it lies on. So now let's complete the table. Radius is 1. The circumference is, well, that's going to be 2 pi times 1. 2 pi times 1. And that's going to equal 2 pi. The circumference does not change. It's always 2 pi. And if the radius is 2, that's going to be 2 pi times 2, which is 4 pi. And then 2 pi times 3, and that's going to give you 6 pi. You starting to see a pattern here? Okay. So now let's see. The length of the intercepted arc. Well, we noticed it was 5/8 of the way around. So it's going to be 5/8 times 2 pi. 5 times 2 is 10. 10/8. That's going to reduce to 5/4 pi. Right? Okay. Now, again, you got 5/8, but now it's 4 pi, right? So times 4 pi. Well, 5 times 4, that's going to be 20. 20/8, that's going to reduce to, and that's 5 pi over 2. And then 5/8 times 6 pi, that's going to be 38, and that's going to be 38. That will reduce to 15 pi over 4. All right. Ratio of arc length to radius, S over R. So we're going to have S, that's going to be 5 pi over 4, divided by the radius, that's going to be 1, and that's going to give you 5 pi over 4. Okay, now let's try it for the other one. You're going to have 5 pi over 2 divided by 2, and that's going to give you 5 pi over 4. And let's do the 15 pi over 4 divided by 3 is going to give you 5 pi over 4. So the ratio is still 5 pi over 4. 5 pi over 4. So what did you notice about the ratios S over R in the fourth column of the table? Well, they were all equal to 5 pi over 4. When the ratios of the values of a variable y to the corresponding values of another variable x all equal a constant k, y is said to be proportional to x. And the constant k is called the constant of proportionality. Because y over x equals k, you can solve for y to get y equals k times x. In the case of arcs that are intercepted by a 225-degree angle, is the arc length S proportional to the radius R? Yes. Yes. If so, what is the constant of proportionality? What is the well, in this case here, it was 5 pi over 4. And what equation gives S in terms of R? So S equals, and that would be 5 pi over 4R. Suppose that the central angle is 270 degrees instead of 225. What would the arc length S? Would the arc length S still be proportional to the radius R? Yes, it would. All right. If so, would the constant of proportionality still be the same? Well, let's see here. 270, let's go to our calculator. 270 divided by 360. Okay, that's going to give us 3 over 4. Okay, 3 over 4. And compared to what was it a minute ago? It was 5/8. So it's going to be 3 over 4. So S would equal S would equal, well, let's see here. Let me try to explain it this way here. It is still proportional. It is still proportional to R. All right. But the constant of proportionality, we'll say K would be, and that's going to be 3 pi over 2. And this is because a 270 degree angle represents 3/4 of a circle, right? For example, on a circle of radius 2, see, R equals 2, S equals 3/4 times, well, S equals 3/4 times 4 pi. Okay. And that equals, well, the force cancel out and you get 3 pi. Okay. So, and S over R equals 3 pi over 2. Okay, here we go. Converting between degree measure and radian measure. For a central angle theta that intercepts an arc of length S on a circle with radius R, the radian measure of the angle is the ratio theta equals S over R. In particular, on a unit circle, a circle centered at the origin with a radius of 1 unit, theta equals S. So 1 radian is the angle that intercepts an arc of length 1 on a unit circle as shown. Okay, at a radian, let me digress a little bit. A radian, we'll do it here in blue. This is that length here, okay? That's the radius, right? Well, if you had a string and you cut here and you cut here and then you laid it right across that, they would be the same length, okay? That's 1 radian, okay? That's 1 radian. All right. Recall that there are 360 degrees in a full circle. Since the circumference of a circle of radius r is S equals 2 pi r, the number of radians in a full circle is 2 pi r divided by r, which equals 2 pi. Therefore, 360 degrees equals 2 pi radians. So 1 degree equals 2 pi divided by 360, which is pi over 180 radians. And 1 radian equals 360 over 2 pi, which is 180 over pi degrees. So here's the formulas. Converting degrees to radians, multiply the number of degrees by pi radians over 180 degrees. Converting radians to degrees, multiply the number of radians by 180 degrees over pi radians. Example 1, I'll let you read and follow on your own, and then when you get back, we'll do B together. All right, glad you're back. 180 degrees over pi times pi over 8. If you'll notice, these cancel out, and let's see, those cancel out, and 180, that's going to give you 225 degrees. Okay, all right. Here we're going to put 180 degrees over pi, and of course the pi's they're going to cancel out, and 3, that becomes a 1, and that becomes a 60. So I get 240 degrees. 240 degrees. All right, now we got 9 pi over 2, so we're going to have 180 degrees over pi times 9 pi over 2. Well, those will cancel out. That becomes a 1, and that becomes 90. 90 times 9, that's going to be 810 degrees. So let's try 180 over pi times, and that's going to be negative 7 pi over 12. So the pi's cancel out. All right. And then 12 into 180, I'm getting negative 105 degrees. And then again, 180 over pi, that's negative 13 pi over 6. So that's going to be 30. And the pi's cancel out. And 30 times 13, don't forget your negative, that's going to be 30 times 13 is 390 degrees. All right, not too shabby. And you can always use a calculator to help you with those. Which is larger, a degree or a radian? Let's see, a radian is larger. A radian is larger. Okay, since it is equal to 180 degrees over pi, and so it's going to be approximately 57.3 degrees. The unit circle below shows the measures of angles of rotation that are commonly used in trigonometry, with radian measures outside the circle and degree measures inside the circle. Provide the missing measures. Okay, let's see if we can do this. All right, there's a little bit of a trick to it. Okay, so this is pi over 2, right? That's pi over 2 right there. Now, half of that is pi over 4. You with me? And that's 90 degrees, right? We know that's 90 degrees. All right. What is 1/3? Okay. What is 1/3? So let's see. 1/2 times 1/3. That's 1/6. So this is going to be pi over 6. Okay. Good. Now this is 2/3 of that, right? 60 degrees is 2/3. 60 degrees over 90 degrees is 2/3, right? Well, 2/3 times 1/2, that's going to give you 2/6 or 1/3. So that's going to be pi over 3. Okay, now this right here is a half a pi, right? This from here to here, that's 0 degrees, and that's 90 degrees. That's half a pi, or a quarter of a pi. All the way over here, that's going to be half a pi. That's going to be 180 degrees. Y'all know that from geometry, right? Okay, so 180 degrees. That's going to be pi. Well, let's see here. If this is half a pi, and this right here, that's 1/3 of that. Well, 1/2 plus 1/3, convert that. That's 3/6 plus 2/6, and that's going to give you 5/6, right? So we're going to have 5 pi over 6 here, right? Okay. Think about it. And then what about over here? What about over here? Okay. So that's, let's see that right there. That's going to be a 1/3. So we're going to have, or it's not, that's going to be 1/6. That's 1/6, right? So what do you got? 1/6 plus 1/2. That's going to be 1/6 plus 3/6, which is 4/6. Well, 4/6 is the same as 2/3, right? So that's going to be 2 pi over 3. So hey, look, we're halfway there. Now think of it. If this is directly opposite of that right there, right? Directly op. So if you add 1/2 to 1/3, let's see, 1/2. That's half. That's not going to quite work out right. Let's see. That's half right. What if we just add a pi to it? What if we add a pi to it? That's not going to quite work out right either. So this is 5/6. That's 6/6. So that's going to make this 7 pi over 6, right? And that's going to be 5 pi over 4. And what is this over here going to be? That's going to be 4 pi over 3. That's 4 pi over 3. That's directly opposite. So think of it, this is 1/3 of pi. If you add another pi, that's going to be 4/3 over pi. This is 2/3 of pi. If you add a pi to that, that's going to be 5/3 pi, right? 5 pi over 3. And this is 5/6 of a pi. If you add another 6/6 of a pi, that's going to be 11 pi over 6. Okay, and that's 270 degrees. All right, maybe that'll help you figure out that. Maybe that'll help you remember. I have a hard time remembering. I have to think about it and work my fractions a little bit. So I have negative 495 degrees, and it says convert each measure from degrees to radians. So I'm going to multiply this by pi over 180 degrees. So those will cancel out, okay? And I can't do that in my head, so I use my calculator, and I got 11 pi over 4. And that was a negative, so that's going to be negative. Let me scoot that over a little bit. Negative 11 pi over 4. Now this is 13 pi, so I'm going to flip this around. I'll multiply it by 180 degrees over pi. So now the pi's cancel out. And then again, I'm not real good at that in my head, so I used my calculator and came up with 195 degrees. All right, good deal. Good deal. All right, solving a real-world problem involving arc length. As you saw in the first explain, for a central angle theta in radian measure, theta equals S over R, where S is the intercepted arc length. Multiplying both sides of the equation by R gives the arc length formula for a circle. For a circle of radius R, the arc length S intercepted by the central angle theta is measured in radians, is given by the following formula. S equals R times theta. Many problems involving arc length also involve angular velocity, which is the angle measure through which an object turns in a given time interval. For example, the second hand of a clock has an angular velocity of 360 degrees per minute, or 6 degrees per second. The angular velocity may also be expressed in radians per unit of time. This makes finding the arc length traversed in an amount of time especially easy by using the arc length formula. So A, the sun. All right, I'll give you a minute and let you do A, and then we'll do B together. All right, B, the earth. Earth's equator is at a latitude of 0 degrees. The Arctic Circle is at a latitude of 66.52 degrees north. The diameter of the equator is 7,926 miles. The diameter of the Arctic Circle is 3,150 miles. A, find the angular velocity in degrees per minute of a point on the equator and of a point on the Arctic Circle. B, how far does a point on the equator travel in 15 minutes? How long will it take a point on the Arctic Circle to travel this distance? Food for thought. Is it easier to get dizzy on the Arctic Circle or the equator? I'm just kidding. I have no idea. All right. Every point on Earth completes one revolution of 360 degrees each 24 hours. So the angular velocity of the points will be the same. Convert the angular velocity to degrees per minute. So we're going to have 360 degrees over 24 hours times 1 hour is 60 minutes. And so 360 times, well, that's going to be 360. 24 times 60, that's going to give you, put it in your calculator, and you get 0.25 degrees a minute. The angular velocity is 0.25 degrees a minute. Multiply the time by the angular velocity to find the angle through which a point rotates in 15 minutes. So 15 minutes times 0.25 degrees a minute is 3.75 degrees. Write a proportion to find the distance to the nearest tenth that this represents at the equator, where the Earth's circumference is pi times 7,926 miles. So 375 degrees over 360 degrees, 3.75 over 360 degrees is x, and then it's going to be pi times 7,926. And we put them all together and put that in your calculator. That's going to be 259.4. So a point at the equator travels about 259.4 miles in 15 minutes. Okay. Write a proportion to find the angle of rotation to the nearest thousandth required to move a point 259.4 miles on the Arctic Circle, where the circumference is pi times 3,150. All right, so 259.4 miles, and it's going to be pi times 3,150, x degrees over 360 degrees. Okay, so multiply across, and then put that in your calculator, and you get 9.437. Use the angular velocity to find time t to the nearest hundredth required for a point on the Arctic Circle to move through an angle of rotation of 9.437 degrees. So 0.25 5 degrees a minute, and t minutes equals 9.437. So t is approximately 37.75. It takes about 37.75 minutes for a point on the Arctic Circle to travel the same distance that a point on the equator travels in 15 minutes. Reflect. How does using the angle of rotation to find the length of the arc on a circle intercepted by an angle differ when degrees are used from when radians are used? Well, when radians are used, you can find the arc length by simply multiplying the radius of the circle times the angle. When degrees are used, you must write a proportion equating the ratio of the measure of the angle to 360 degrees and the ratio of the unknown arc length to the circumference of the circle. Then you can solve for the arc length. So let's see here. When radians are used, you can find the arc length. By simply multiplying the radius of the circle times the angle. When degrees are used, you must write a proportion equating the ratio of the measure of the angle to 360 degrees in the ratio of the unknown arc length to the circumference of the circle. Then you can solve for the arc length. Then you can solve for the arc length. All right. Our turn. Astronomy. A neutron star, an incredibly dense collapsed star in the Sagittarius galaxy, has a radius of 10 miles and completes a full revolution every 0.0014 seconds. Find the angular velocity of the star in radians per second. Then use this velocity to determine how far a point on the equator of the star travels each second. How does this compare with the speed of light? About 186,000 miles a second. Okay. Let's see here. Find the angular velocity. Find the angular velocity. Okay, that's going to be 2 pi radians. And that was 0.0014 seconds. And that's going to be approximately 4,490 radians second. All right. Distance the point travels in a second is the arc length it traverses in a second. So S equals R theta, which is 10 times 4,490, which is approximately, well, we'll just say 45,000. All right. So the point travels about 45,000 miles around the star's axis in 1 second. The point travels about 45,000 miles around the star's axis in 1 second. About misspelled second. All right. Let's see here. Because 45,000 over 186,000. That's about 0.024 in the calculator. So this is about 1/4. Is about 1/4 the speed of light. All right, and I got the 186,000 from there. I didn't know off the top of my head. Geography. The northeastern corner of Maine is due north of the southern tip of South America in Chile. The difference in latitude between the locations is 103 degrees. Using both degree measure and radian measure, and a north-south circumference of the Earth is 24,860 miles. Find the distance between the two locations. So let's see, 103 degrees, and it's 360 degrees, x miles, and that's 24,860 miles. Okay. Cross multiply and you get 360. X equals 103 times 24,860. And then I guess you're going to want to divide by 360. So you got X equals 103 24,860 divided by 360. And that's going to be approximately 7,110. Okay, that's using degrees. That's using degrees. All right, using radians. All right, first convert radians. So we're going to have pi over 180 degrees times 103 degrees. So the degrees will cancel out. and you're going to get 103 pi over 180. All right, so S equals R theta, and that's going to be 24,860 over 2 pi times 103 pi over 180. Pi's will cancel out. And that gives you, put it in your calculator, 7,110. So the distance is about 7,110 miles. Pretty cool, huh? All right. Given the measure of two angles of rotation, how can you determine whether they are coterminal without actually drawing the angles? If the difference between the two angles is an integer multiple of 360 degrees or 2 pi radians, they are coterminal angles. So if the distance between the angles is an integer multiple of 360 degrees or 2 pi radians, they are coterminal. Cool. All right. What is the conversion factor to go from degrees to radians? Well, degrees to radians would be pi radians over 180 degrees. What is the conversion factor to go from radians to degrees? Well, that would be 180 degrees over pi radians. How are the conversion factors related? They are reciprocals. Think about it. If you multiply the two, that cuts out, that cancels out, that cancels out, and that just leaves you with one. Cool. Essential question check-in. An angle of rotation in standard position intercepts an arc length of arc length 1 on the unit circle. What is a radian measure of the angle of rotation? What is a radian measure? It would be 1 radian. Okay. The angle of rotation that intercepts an arc whose length is 1 on this circle has a measure of 1 radian. All right. Great lesson, folks. See you tomorrow in class, and y'all have a great evening.